Hi, everybody. My name is Dr. David Jacob with Science Education Innovations, and this channel is going to be dedicated to the next generation science standards. So, in this series, I'll be working through a number of different topics, and we'll get through them one by one. So in episode one, we're going to talk about the new science standards, and I put up NGSS and NYSSLS. I'm currently residing in the state of New York, and I'll be talking about the New York State Science Learning Standards, which are very similar to next-gen science standards, but we'll talk about it a little bit at a time. So why bother listening to me? Who is this guy and what does he mean? So I started working with the NGSS standards in 2013, just as they were released. And in that time, for the next 10 years, I worked developing the K to 5 science curriculum called Science 21. So with that group, I worked with a veteran group of educators, both elementary teachers and science specialists, to create this curriculum. During that time, I also wrote children's books and informational texts to support these core science ideas. In addition, in my work in the last 10 to 11 years, I worked with middle school and high school teachers to develop lessons or units or series of study around that. We developed phenomenon-based learning, we developed curriculum design templates, and I created professional learning experiences for those people. I coached middle and high school teachers, and my current position, that is what I'm doing, working with middle and high school teachers. And I was a professional developer in New York State, in Texas, and nationally at NSTA conferences, the National Science Teaching Association in Los Angeles, in Chicago, in Philadelphia, Atlanta, all across the country. And most importantly, I was a classroom teacher for 15 years. So how were these standards developed? And I think one of the things we need to talk about is who developed them. With the Common Core state standards that were released about the same time, they were developed by the Board of Governors. What's different about this is this project started back in the 90s with the American Association for the Advancement of Science with something they called Project 2061 and Science for All Americans. So Project 2061 was designed to say in 2061 we would have all Americans scientifically literate. This led to something called the Benchmarks for Science Literacy, once again in the 90s, which led to the first version of the National Science Education Standards. These were mostly ignored across the country, except for me, which means that I actually, in New Jersey, started to work around them and I started developing units of study around around these standards. In July of 2011, a framework for K-12 science education was released by the National Research Council. And that became the foundation for what became the next generation science standards. What's most unique about this is it was prepared by a group of scientists and science educators, including Nobel laureates, to create what was there. Here's a brief overview of who was on that committee. I want to highlight two people on this list. One is Dr. Joe Krychek, who led the physical science team and is currently a rock star of NGSS and is creating curriculum right now. And Roger Bybee, who was a legend with the BSCS curriculum out of Colorado Springs that is also known for the 5E model. And these people were the foundation for who wrote these standards and why these were important. So we're talking about people who were really involved in science education, not ancillary. So this committee of 18 people really that were recognized in their fields of science or in science education started to reorder what they thought was really important. And the reason why I say that is sometimes with the next generation science standards, people say it's a watered down version of science. What it was is actually a core idea, and the goal was science for all Americans, not just for scientists. So what this really means, this next gen science standards, is it's to reflect a new vision for science education in the United States. So we want to keep that in mind as we go through that. And this document, the framework for K-12 science education, can be downloaded from www.nap.edu, and it's free for you to download, but it kind of is the work that went behind the standards. So this is a general view of what happened. If we look at this 2011, 2013, knowing that we're starting here in 2025, today that I'm recording this, and that means the release of the next gen standards. In New York State, several years later, we adopted the New York State Science Learning Standards, and there was a strategic plan by our state education department about these 5 elements in their strategic plan. So if we look nationally what's happening with these standards, this is a current adoption of either the next generation science standards in those purple states, or in the turquoise states, standards based on the framework. So in New York State, we are not an NGSS state, but we have adopted something based on the framework, which is what is actually written into our standards. And a lot of those other states that are also in turquoise will look at that. So for most states, they did not adopt NGSS, but they are making adaptations. So a lot of what I'm talking about in this video goes for either you're an NGSS state or a framework influence state, but we'll kind of talk through what the real vision is for this. So what's really different? The principle of the framework in one of the first chapters, you can see on page 24, 29 of the framework, is the children are born investigators. That means that when you are teaching science, students really want to learn about science in general. And one of the other principles of the framework is that we're focusing on core ideas, not the details that we might have focused on before, but the core science ideas that can be brought into, that can be explain multiple things at the same times. Also, we're talking about the science and engineering practices, which there are 8 of those, and science of the cross-cutting concepts, which are designed to be across disciplines within science, but for elementary teachers, it can be across disciplines within ELA, social studies, math as well. So one of the other foundations of the framework is that you don't learn something in a week and then hold on to it forever. What you are doing is that understanding develops over time. So these standards were designed to be a K-12 initiative, and if you really look at, which we'll look at slightly later in this video, of a connection between the K1, K2 band, the 3-5 band, the 6-8 band, and the 9-12 band. So science and engineering require both knowledge and practice. So that means that students should be practicing science, not just learning about it, but the knowledge is still important as well. And connecting to students' interests and experiences is really important. How do we make what we're doing in our science classes applicable to students' lives? So these 5 principles of the framework are really important. So when you're thinking about why we're doing this change, it's not just here's new standards, let's do something new. This is really a change in what we're looking at and how we're approaching it. So I couldn't do any video about NGSS or NYSSLS without talking about the 3 dimensions, and they are the science and engineering practices, the disciplinary core ideas, and the cross-cutting concepts. At this point, we're really know that these are out there and people should be familiar with these 3 elements of the standards, but I will talk about them anyway. So there are some key learning ideas that we are talking about here, and the first one is that learning challenging concepts develops over time. So when we're talking about students being able to develop what they're learning, they need the time to be able to do that. And we're moving from a point of knowing about or just having an information frame to a sense-making frame, which is really students figuring out things. So that's an important change in what we do in our classrooms, not just a matter of knowledge transfer, but the students actually doing it. So here are the 8 science and engineering practices. We'll do videos on some of these a little bit later, but I wanted to highlight the differences between 2 of the practice, one which is asking questions in science, but the companion to that practice is defining problems in engineering. And in science, after we ask questions and we do a lot of stuff like plan and carry out investigations or use models or look at the mathematics or collect and analyze data, we then construct explanations. So we ask questions to construct explanations in science. In engineering, we define problems that we then do a bunch of stuff and we design the solution that goes with it. So in our disciplinary core ideas is, once again, it's not the details that we're looking at. We're using details in classroom, but we want students to take away core ideas. And that's an important part of this. So it's their progressive from K to 12, which is important, and their links between the disciplines. So life science connects to physical science connects to earth space science. So if you look at this quote from the framework as well, it is that students continually build on and revise their knowledge and abilities over multiple years. So when we think about what we're doing here is kindergarten leads to grade one leads to grade two, lower elementary leads to middle school leads to high school. We've known that for a very long time, but this is now explicit in our standards. The third dimension is our cross-cutting concepts. These are the 7 cross-cutting concepts, and once again, we'll unpack those in other videos, but I wanted to just talk about them here. One of the foundational documents that you should be able to find on the NSTA website is this matrix of the practices that we should be working on unpacking throughout our work. And one of the things that we want to look at is that the SEPs are not just bumper stickers like, oh, we're arguing from evidence. There are very specific elements that go with this. So if we're looking at engaging an argument from evidence, we are looking to construct, use, and or present an oral and written argument or counter-argument based on data and evidence. So those elements are what we should be doing, and we design instructional tasks or we create prompts for students to be able to demonstrate their ability to do that. We may never have done that before. Our focus was on content, and now we're changing our focus a little bit to include practices and cross-cutting concepts. So the same thing goes with our cross-cutting concepts. They're not just headlines. So if we're looking at cause and effect, what we're really looking at in cause and effect, not generalized cause and effect, but cause and effect relationships can be suggested and predicted for complex natural and human design systems, and by examining what is known about smaller scale mechanisms within the system. So that is a very specific action that students should be able to do, both a cognitive and a physical action, and we want to be able to have students do that. So in a standards page, this is the New York State Science Learning Standard. So it looks very similar to our NGSS, but this is a performance expectation. MS stands for middle school, PS stands for physical science, and 1-4 stands for the code that we use for that performance expectation. And if you look at the 3 dimensions below, the blue, orange, and green, in our science and engineering practice, I've actually highlighted the code that says this is the element, just like I showed you before, of what we're trying to achieve in this performance expectation. And the same thing goes with our cross-cutting concept. It is this cause and effect cross-cutting concept is attached to this performance expectation, and this is what we're expecting students to be able to do in that. And then if we look at the disciplinary core idea, this is the explanation that goes for, or the DCI connection that goes to this performance expectation. So once again, I'm talking about New York for a moment. If you see that NYSED, New York State Education Department, this was added. So if you're in a state that is not an NGSS state, you have to look at your standards very closely and recognize if you're adopting a curriculum that was not built by your state education department or somebody designing it just for your state, you may need to make adjustments to what you're doing and add or delete things from that curriculum in order for that to be able to work. So in New York State, once again, these highlighted ones, if you see that this MSPS 1-7 is highlighted in yellow, that means that was not in Next Generation Science Standards, but it was only in the New York State Learning Standards. So what does this mean? A performance expectation integrates the 3 dimensions, the cross-cutting concepts, the disciplinary core ideas, and the engineering practices, much like a cord, a multi-stranded cord, and they work together to create the performance expectation. And then the thing that's really important about our other performance expectation is that we're expecting students to demonstrate knowledge and use. So I've been using the language that says it's not just about content or their disciplinary core ideas, but what do students do? And we want to be able to see that their knowledge and use is available to them. So I'm going to show you a progression from K2 to 3.5 to 6.8 and to 9.12 along a single strand of performance expectations. So if you look at the elementary one here in K2, this is a first grade standard, and it says use materials to design a solution. Here's our 3 dimensions working here. But we're talking about to human problems about by mimicking how plants or animals use their external parts. So if you look at the disciplinary core idea that we have up here, it says that LS1 dash A is structure and function. So within our performance expectations, we're looking at parts. So in K to 2, we're looking at external parts. At 3 to 5, we're looking at external and internal structures that support survival, growth, and behavior. In the middle school, we're looking at how living things are made up of cells and how they have different types of cells. So once again, the structure of the cell and what is the specialization of those cells. At high school, it shifts a little bit to the structure and function of DNA and how does the structure of DNA create specialized cells and proteins in that thing. So there really is a K to 12 progression, and we want to be able to look at those pieces. So you can see that I also have over here on the right-hand side, I'm keep having to shift myself from left to right, is that there are different cross-cutting concepts. So even though there is a similarity between these performance expectations, the science and engineering practice or the cross-cutting concept might change. So, what does contemporary science education mean in 2025? So, I borrowed this phrase from my good friend Dr. Oki Lee out of New York University, who coined this phrase, and I love it because it says it's not just new, it's not just modern, it's what we're doing contemporary in 2025. So, science literacy, as we talked about, is not a list of facts, but a habit of mind that happens over time. And teachers need to support and encourage the development of new understandings in students so that they can deal with these challenging standards. And science education is not just a lecture or a bunch of fun activities, but it is sense making with both hands on and minds on tasks for deeper understanding of our science that's out there. So sense making is a really important term for us to do. How do students make sense of science, not just memorize and regurgitate? And scientific literacy requires practice, reflection, and cognitive engagement. Sometimes we give students low-level science tasks. Even if it sounds complicated because it's big science words, we want them to really cognitively engage with this, and we want them to reflect on their work, and we want them to practice that. So here's one of my favorite quotes from one of my favorite scientists, Albert Einstein, that information is not just knowledge, it is also a source of knowledge is experience. So giving students the experience to really gain knowledge, you need experience to gain wisdom. So let's hear from Albert Einstein as part of our marching orders in this area. So this isn't just a change of standards, but this really is a change of teaching and learning. And I don't say pedagogy, I talk about teaching and learning because it's not just what you are doing as a teacher, but it's what our students are doing as well. So we're looking for, instead of having teachers deliver science information from teacher to students, we want to look at this as not just a knowledge transfer, but we want to flip this script and we want students to do sense making so that they understand the science information. So we're not just talking about science information being memorized, but we're talking about understanding and really sense making of science standards. So let me give you an example of what I mean about this. So here is a diagram. We could call it a model. This is a diagram of a particular thing. What is this thing and what are we trying and how does it work? So students can memorize and know all of the pieces. They go through and they memorize the bits, and then you on your quiz black out all of those words or white out all of those words and you go fill in the blanks. And the kid who gets all of them right gets 100, and the kid who gets 50% of them right gets a 50% on their quiz. But do they know anything about this device or what it works? For those of you who have a keen eye, you can see that it is a milling machine. So when we think about this thing, what is this thing and how does it work? Have we done the same as we did here? Do the kids know all of the parts of a cell, but really doesn't know what it means? So we can have kids memorize a cell diagram or a cell model and not really understand what it is. So some of us might have memorized our way through science and we were rewarded for that. Now we are looking at something very different. So once again, from the framework, I use this model to talk about what's really different here. So what we're looking at investigating information or investigating science, evaluating information, and then developing explanations and solutions. So in the real world, we ask questions, we make observations, we experiment, we measure, we do all of those things to collect data. And then we start testing our solutions or testing our thinking around that. And then when we've done our testing piece or investigation phase, we start evaluating. Do I understand what the data means? Can I construct an explanation of what this data means? Is my information accurate? All of those things, and we critique ourselves and we analyze and we argue with ourselves, or we argue with our small community. And then what we do is we make it public. And those public is when we start to formulate models or we formulate theories. And when we look at this, we can imagine, we can reason, we can calculate, we can predict, and we actually formulate hypotheses or propose solutions to engineering problems that we've looked at. So this is one model for us to look at. And here's another model that you may consider, that when we look at the natural or designed world, we start to use our investigating practices, like asking questions and planning and carrying out investigations to collect data. And then we make sense of that. And how do we make sense of it? We use models to make sense of our data or our questions. We analyze data, we construct explanations, we get some good ideas. And then what we do is we throw it out to the larger community and we start to critique. Is our thinking accurate? That could be the teacher, could be the classroom. In the science world, it's putting out journal articles. But when we're looking at what we're talking about from a science perspective, we're engaging in argument from evidence and we're obtaining, evaluating, and communicating ideas to the larger group. So there are four literacies for you as a teacher. And what makes this so hard is these four literacies have to happen simultaneously in your brain as a teacher to achieve these new standards. So the first one that we're looking at is the standards language literacy. What do the standards actually say? What are they asking us to do? And we tend to jump right to our content knowledge and explain it that way. But we really have to look at three dimensions, and maybe it's different than what we did. So that's a deep dive, and we'll do that in another video as well. So science idea literacy. So once again, we've learned a lot about science, but we learned generally about biology or chemistry or physics or all of those things. Did we really do a deep dive? No, we learned certain things that were canon to our subject area, but now we're looking at application. And sometimes in the application phase of science, it becomes a little bit more complicated. So we want to make sure that we understand our science ideas. So our inquiry pedagogy literacy. How do students do inquiry learning, or how do students do sense making learning? How do I teach through sense making, not just an information lens? That is a really big shift for us, and we have to look at what we're doing. And then I'm going to call understanding by design. Understanding by design is a curriculum design method. There are lots of them out there. There's 5E, as I mentioned earlier, or there's GRC. There is lots of different curriculum models that are out there. But all of them start with what is the end in mind? What is our standards asking us to do? And how coherent is one lesson into the other? Or have we chopped up our learning into little pieces? We want to be able to do more of that. So in my last 10 years of working with teachers, there's been a major mind shift for teachers. So here's a collection of things that I hear from teachers on a regular basis, and here are some of my answers to those. So, but the students have to know this piece of content. Why? Remember, we're looking at science literacy for all Americans. If a student can't remember a contact fact for your test, how likely are they going to remember it a year from now, or 2 years from now, or 5 years from now? So what good is it that we're getting kids to memorize content facts as opposed to disciplinary core ideas? So we want the kids to relate to lots of different things, but our number of disciplinary core ideas are minimal. How do we keep on going back to that? But they will need this for college. Why? Is every student going to college? Is every student going to college for biology or chemistry or physics or for earth science? We have to really understand what the students' goals are. And once again, in those college classes, they're going to reiterate what you did in high school. So they're going to have to go back and do it again. For you to be able to get them to figure out things is really the more important thing. Well, this is the way we've always done it. Well, maybe it's time for us to review. This is 2025. The world has changed around us. AI is out there. How are we really doing the work of the world? It's not the world that you went to school in. We're now changing what we're doing. We need to change. And what evidence do you have that the way you've done is always right? Is it because you got good test scores? There is lots and lots of research. The framework is actually filled with lots of research about how students learn science, and it might be worth us challenging ourselves to see if how we're doing it or how we're teaching is still scientifically reasonable to what students are doing right now. So if we look at our mindset shift, we're going from memorizing science facts or conveying knowledge to applying scientific practices, applying core ideas to multiple different scenarios, and using cross-disciplinary concepts to actually help us understand new situations. So it's really a bit about application of our science understanding, not just regurgitating what we learned in class. And not about conveying knowledge, but students constructing knowledge and understanding, and once again, doing that sense making that we're talking about. So what's really different? Phenomenon-based learning allows students to look at some unique science situation or phenomenon that's happening, and students use their practices and their cross-cutting concepts to figure stuff out. So how will these standards be assessed? I'm going to do a lot about assessment later, but I wanted to just talk briefly. So if you haven't already seen this, the Council for Chief State School Officers have published a beautiful document about assessment frameworks that have been used by state education departments in New York State. This is actually one of the documents that they were using to create their new Regents exams in New York State. And if we look at this, it's about item clusters. So a single question of fact information is not necessarily what we're looking at in most states anymore, but we're talking about a stimulus and a series of items that go to that stimulus. And those stimulus or those items can be a combination of a DCI and a SEP, or a DCI and a cross-cutting concept, or all three of them at the same time. It's very hard to write three-dimensional assessment items, but very often at least we have two in that. So this is another resource from Dr. Harris, Krychek, Pellegrino, and DeBanger. And remember, Dr. Krychek is one of our NGSS All-Stars, and he talks about what this is. In New York State, they actually reference this article to say this is what we're doing, and this is a very complicated model, but you can go back to it at some point. But they're creating integrated dimension maps and then articulate learning performances. In New York State, that actually became our performance level descriptions that the state assessment writers are actually using to write a level 4 question or a level 3 question in New York State, or in those PDs. So I wanted just kind of to do this overview. This is a little bit longer than my typical videos will be, but thanks very much for watching. Please like and subscribe to this channel, and there'll be lots of more videos as I progress in the next couple of months. And if you have something you want to see, write it in the comments, and I'll be reading those comments to be able to say how else can I inform you. Thanks very much, everybody, and have a good day.